Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage. This beautiful crystal of sodium chloride is a solid at room temperature, and you need a hammer to shatter this crystal, which would be a pity. I wouldn't have the heart to do that. In order to vaporize a crystal of salt, you need 1400 degrees Celsius, the hottest part of a Bunsen burner flame. On the microscopic atomic level, its ions are held together by attractive forces between the positively charged sodium cations and the negatively charged chloride anion. To separate these ions, you need 783 kilojoules per mole. So to vaporize 3 tablespoons of salt, you need to focus the energy of over 1,000 watts of power onto the solid for over 10 minutes. Yet, when you put salt in water, these ions are separated with barely any change in temperature. In fact, the water will get a few degrees cooler as this happens. How are these Coulombic forces of attraction and the ionic compound overcome? It's all explained by the fact that water molecules have their own partial charges. Even though the water molecule has no net charge, the water molecules are polar. They have a negative side and a positive side. When a crystal of sodium chloride is placed in water, the partial positive charge of the hydrogen ends of the polar water molecules attract the negatively charged chloride ions and gradually surround them. And the partial negative charge of the oxygen ends of the water molecules are attracted and surround the positively charged sodium ions. The new dipole ion bonds form, and the hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution. This is part of the AP Chemistry curriculum, and you'll find questions on the exam on this topic. Here's a question similar to one that you would find where you're given an illustration of a water molecule and a lithium chloride crystal, and you're supposed to make a drawing where you identify the ions, okay, that's our lithium chloride crystal, and the arrangement and proper orientation of the particles in solution. To get the points for this problem, you had to identify the lithium ions as being positive. They're the smaller ones. They've lost the electron. We'll deal with size of ions later. And here's the chloride ion with a negative charge. They show the larger one. Then, once you've identified the ions, you had to show how water molecules would hydrolyze them. Notice which they identified the negative and positive dipoles, and they've got the negative part of the water molecule attracted to the lithium ions. In this case, they got 4 of them. They show that attraction and bonding with the dashed line, and they have the water molecules attracting the chloride ions with their positive dipoles towards them, and of course the dashed lines. That's how you end up answering a problem like this.